So we now have Andrea Righi, who's going to give a talk on Rust-ifying the Linux kernel scheduler. So please give it up.
Hello?
Yes.
Okay, yeah. You can hear me, I guess. So, yeah, we're going to talk about scheduling, kernel scheduler, but in Rust. How many kernel developers are here, or people that have played with the kernel? A few, okay, that's good. Okay, you don't need to understand the kernel. That's a good thing. Yeah, so here's the agenda. I want to go to the cool stuff, but before going to the cool stuff, I need to tell you something about scheduling in general. And then we see how we can use this technology called sched-ext to basically implement a scheduler, kernel scheduler in Rust. But first of all, what is a scheduler? So a scheduler is a kernel component that determines where each task needs to run, when, and for how long. So it seems fairly easy, conceptually speaking, but in practice it can be really hard. Scheduling is a very non-trivial problem, in particular because there are different architectures, different workloads, and it's really difficult to model a scheduler that works for everyone and in every possible scenarios. So the challenges are fairness, if you want to design a scheduler that is generic as possible, because you need to give each task some chances to run. After a while, like, it's difficult to model something so generic. Now, so what's the situation in Linux? The policy in Linux is to maintain just a single scheduler, or one scheduler to rule them all. We used to have CFS before 6.6. Now we have another scheduler called eBPF. The first one is like, the CFS stands for completely fair share scheduler, or completely fair scheduler. And it's based on fairness from the previous slide. So it gives each task, it's doing weighted bandwidth allocation to tasks. That's it. We moved to eBPF. eBPF is a deadline-based scheduler. Deadline allows to perform better in latency-sensitive workloads, so it's for latency. But I'm not going into details of these schedulers. If you're interested in some details, there's another talk tomorrow in the kernel dev room where I'm talking more about these schedulers and how play in video games. But anyway, the fact is that there's just one scheduler, and therefore it's really difficult to conduct experiments, because if you want to do some tests or some experiments with the Linux kernel, you need to patch the kernel, recompile, reboot the system. It's not always easy to do, especially in production. Even rebooting in production, if you think at like large cloud environments, you reboot, you need to rewarm the caches, you have a downtime. So really difficult to conduct experiments, and it's really difficult to upstream changes, because you may find something that works really well for you, but if it doesn't work for anyone, your change is not going to get merged, because you may introduce regressions. So the single Linux kernel scheduler is like, there are compromises. It's trying to do the best, and it's the best generic scheduler that we may possibly have. But sometimes, you may want to relax some constraints and say, I'm willing to accept to have like an unfair scheduler just to solve my problem. And right now, in this situation, it was impossible to do that, unless you maintain your own scheduler. There are big companies that can afford that, even if it's painful for big companies, because maintaining a patch so impactful as the scheduler, it's not a joke. It's quite time consuming. So here comes sched-ext and BPF. Sched-ext, for those that don't know, is a new technology in the Linux kernel that allows you to implement a scheduling policy as a BPF program. And it needs to be GPLv2, by the way. It's not like a soft requirement. Actually, the BPF verifier would not accept your scheduler if it's not licensed as GPLv2. So BPF, for those that, I think you're all familiar with BPF. I don't want to go over. No, okay. BPF is like a JIT in the kernel. You can see BPF as like kind of a virtual machine, and you can write programs in C, for example. Powerful because you can test things, you can test changes to the kernel without crashing the kernel, so it's safe. Of course, you can't write things arbitrarily in kernel memory, but you get read access to kernel memory. And sched-ext leverages BPF to give the connections to the scheduler callbacks. So the scheduler in the Linux kernel is implemented like as a class or as a struct of function pointers, and those function pointers are via sched-ext are redirected to the BPF program. And that's how you can like write a BPF program that implements certain callbacks that are called by the sched-ext technology, and that's how you can implement your scheduling policy in BPF. So of course the benefits of this technology are the fact that you can design custom schedulers. You can load them at runtime. You don't need to recompile the kernel or reboot. You just start the program. And of course, this leads to rapid experimentation. Usually, when you test a program in user space, you edit, compile, run, and then edit, compile, run. So the turnaround of this edit, compile, run cycle is really fast in user space. It's really slow in kernel space because you need to reboot and whatnot. But with this technology, you have the same feeling of developing like a user space application, while instead you're actually changing kernel code, in particular the scheduler. So how does it work? Well, there's a kernel component that runs in the kernel subsystem called sched-ext. And in BPF, you just need to implement a few callbacks. For example, there's a callback called enqueue that is invoked every time that a task wants to run. There's a callback called dispatch that is invoked every time a CPU is ready to accept tasks, and so on and so on. So implementing these callbacks allows you to write a program in BPF that implements a scheduler. But like I mentioned, there are restrictions because BPF, in order to provide this concept of safety, there's this project, Rust for Linux, that tries to bring Rust into the kernel. Here I'm trying to do the opposite. I'm trying to bring the kernel into Rust. Because Rust for Linux is controversial. This is even more controversial, right? So here's the idea. I had to give you a little introduction about sched-ext and BPF just to explain this slide. Basically, so my idea was like, what if we use sched-ext to implement a BPF scheduler that does nothing except to bounce all the scheduling events to a user space program? Because a cool feature of BPF is that the user space program that loads the BPF bytecode via the BPF syscall shares the address space with BPF. And BPF provides some data structures that are called maps that can be used like a message passing interface between BPF and the user space program. So the idea is like, let's write like a minimal layer in BPF that just bounces the scheduling events to user space. And then the user space can take all the scheduling decisions. So you actually implement the scheduler in user space, You pass the results of the scheduling back to the BPF, and BPF will do the actions that are decided by the user space program, pass everything back to the kernel. And in this way, we have offloaded the complexity from BPF into a user space program. We can still load and unload a scheduler at runtime using the usual, BPF scheduling way. But we have a user space program now. So that's like, microkernel vibes here, because we're actually moving part of the kernel into user space. The consequence, a good consequence of this is that now we have unlocked the access to any kind of libraries and languages, because if the kernel scheduler is a user space program, I can write this user space program in any language. I can write it in Python, in Java, in Rust, for instance, and I can use all the user space libraries. In Rust, we use crates. I can use any kind of crates and whatnot. So, yeah, we have seen like the previous slide where there was only the left part. Now we have also the right part that is basically the scheduler. And what I'm doing is like the BPF scheduler will share data. It is only implementing this kind of message passing interface. And it uses libBPF, which is a C library. But there's also libBPF-RS, that is the Rust binding to BPF. So user space program, user space scheduler becomes the program down here. Where am I? Here. Down here. And and this is like a regular Rust program. I can literally cargo build this thing and run, and it will replace the in-kernel scheduler with my program. And so as a proof of concept, I implemented a scheduler that is called Rustland. Because initially I implemented, there was a scheduler called userland that was written in C. So I decided to do the same with Rust, and it's called Rustland. The scheduler itself, it's a deadline-based scheduler, so it's better for latency. It's not fair in opposition to the in-kernel scheduler. It's very unfair. It prioritizes latency-sensitive work tasks a lot. But that's like the implementation of the scheduler is like it's a secondary goal. I just wanted to prove that it was possible to implement a kernel scheduler in user space using this technology. So this is more like a proof of concept. It's supposed to be a proof of concept. And I tested this with like a video game, because like I was like, well, video game is cool. Let's see how fast a video game can go if I replace the Linux scheduler with this complete mess that is moving everything to user space. And like I was expecting to do like, I don't know, 5 FPS or something like that. But then I actually posted this video. I was showing that this unusual workload where I'm playing Terraria, it's a video game, while building the kernel, which is not something that you usually do, because if you're a gamer, I mean, you want to do gaming, unless you're also a kernel developer and you build the kernel in the background. But so the part on the left, the eBPF, is the kernel, is the in-kernel scheduler, the default Linux scheduler. And there's this video that's also available on the sched-ext website, and shows that the game is very choppy, and it's doing like 26 FPS. But it's not just choppy, it's also very inconsistent. So it goes from 10 FPS to 40 FPS, sometimes 30, 20. So it's a really bad gaming experience. And with the user space scheduler, with the Rust scheduler, it's doing 60 FPS, which is insane. But the thing is, like, it's just the scheduling algorithm that is different, and it's overly prioritizing latency-sensitive work. So it's just the scheduling. But that was to prove that not that the scheduler is better, because it's better for this particular use case. It's worse for everything else. But the point was, it's possible to implement user space schedulers that can outperform the in-kernel scheduler, which is an interesting thing. Like, and this one, you don't have to recompile the kernel. You just insert and it works. I was actually planning to show you a demo, if I can. Let's see if I can. So we have this fish tank. This is the default scheduler, okay? Let's see what happens if I start. Do you see it? Okay, yeah. Let me try to build a kernel. That's the same example, but you know, showing live, it's more cool. Okay, you see, right? The FPS goes like 9 FPS. It's really bad. Now I should have here. Sorry, I prepared everything in advance, but I had to reboot. So, okay, let's do. So Rustland is the scheduler. Okay, now let's go back to. Okay, I start the build. I'm doing 10 FPS. Now I just start this program down here, which is the. Okay, now the Rust scheduler is going, and you see it's going 40 FPS. And you know, I don't care if the scheduler is not fair. So if I stop the program, you see that it's going back to the bad performance. Start the program again, and it's okay, going back to. So I can, if you imagine doing this by changing also the scheduler, this is really powerful because you can literally do this in production. If I intentionally insert a bug in my scheduler, there are two things. There's a verifier that if there's a memory problem, it won't load my scheduler. So I can see if it's actually faster now. That's the switching slide. No, but the thing is, so why is it better? What is happening? Is it because Rust magic? No. Yeah. Someone said yes. I wish I could say yes, but unfortunately the answer is not really. So the trick is in the algorithm, right? It's not in the language. The algorithm is different, and you can see here. This is Perfetto. Big shout out to Google for making this tool, which is amazing. It helps you tracks all what happens. Like also on the y-axis, you see all the CPUs. On the x-axis, you see the tasks. The yellowish one is Terraria. It's like the main thread, and you can see that at the top, that's the kernel scheduler, is trying to be fair with all the tasks that are running. So all the Clang that are compiling the kernel, and also the main Terraria task are, you know, it's fair. It's a fair scheduler. So there are certain logics, like it's still deadline based. So there are certain logic to prioritize latency for the Terraria task, and you can see that. You know, periodically it gets some CPU time. But down below, Rustline is just doing a lot of time to the main Terraria thread compared to the other tasks. It's also a lot more bouncy, like it's constantly bouncing the task here and there, which probably is not a good idea, because for cache locality this is bad. But, you know, it's trying to find all the possible free slots, and it's very work conserving. So it's, as soon as there's a CPU available, you can see that it's trying to schedule the main game, the game thread into the CPU that is available. So that's why it's working better. But like, what's the power? What's the benefit of Rust? What's the powerful thing about Rust? Because I thought, okay, this is a cool idea. Why don't I generalize this And can I make like a crate that people can use to design, to write their own scheduler? So I generalized the backend of this Rustland scheduler, and I implemented a Rust crate that is called sched-ext Rustland core, which is available in crates.io. And you can use this like as a, you don't have to learn like all these sched-ext and eBPF boilerplate. It provides an easier API. And the cool thing is that you can literally like cargo init your project. You use this crate, and I also wrote a template, so you can literally git, it's on GitHub. You can git clone the template, and yeah, just cargo build that. And the template implements a FIFO scheduler using the Rustland core crate. So it's a really easy to understand template. And in this way, you don't have to learn anything about the underlying layers of sched-ext and eBPF, kernel. It's a very abstracted interface. And I think I have, okay, that's the design. Basically, it's more in details. We have the callbacks here that are implemented, this is the eBPF part, and the crate contains a backend which implements the eBPF part, and then it's using the eBPF RS to implement a front end, and your program is here. Whoops. Yeah, so this is cool. I wanted to show, like, this is a working FIFO scheduler in sched-ext, implemented in sched-ext Rustland core, which fits in a slide. So I thought that was a cool achievement. This is a kernel scheduler. Like, we can run this, and it's like, yeah, I can show you this. Like, it's in Rust scheduler. So this program that runs here, it's printing some statistics, but basically the code is this one. And right now I'm doing this presentation running a FIFO scheduler implemented in Rust. And what it's doing is just, the queue task is just consuming task that wants to run. Select CPU is telling the backend, like, give me a CPU that is available, is idle. And I assign the task, the CPU to the task. If select CPU doesn't give me a CPU, I tell the backend, just dispatch this task in the first CPU available. Then I assign a time slice that is inversely proportional to the amount of tasks that are waiting waiting to be scheduled, and then I dispatch the task in order. That's it. Like, that's a kernel scheduler written in Rust that fits in a slide. I think it's pretty cool. And yeah, if you have questions. Actually, no, these are the takeaways. No, I told this already. Like, the important part here is Rustland is not a better scheduler in general. It's just a proof of concept to show you the potential of this technology that you can use it, literally use in production to do scheduling, testing, which never happened before because scheduler was a very monolithic part in the Linux kernel, difficult to change. Rust itself doesn't make the scheduler better, but having access to Rust, especially in user space, allows you, to use the whole language without any restriction. It's not like Rust for Linux that still has restriction. It needs the proper abstraction to be implemented in the kernel as kernel code. This one, you're actually in user space, so you don't have the Rust for Linux restrictions. It's easy to experiment because it's like writing, I mean, the FIFO scheduler fits in a slide, and you just need to compile and run and stop it whenever you want. And potentially you can import any other crate that you have access with a regular user space program. You can import libraries. Maybe, I mean, if you're crazy enough, you can plug an entire AI or a large language model in this program that decides your scheduling. It's going to be more CPU expensive than the task that you're trying to run, but, I mean, that's like, yeah, sched-ext. There's a logic that says, if nothing is running, dispatch the user space scheduler in the first CPU available, and you know, the user space scheduler will have like a queue internally with all the tasks that are waiting to run. So it's scheduled by the BPF program, it runs, it tells the BPF program, like, okay, this guy goes here, then go. And then BPF tells sched-ext the results, and the scheduling happens. But it's a good question. It's the BPF backend that decides to schedule the user space program.
How can you tell that Terraria has tighter deadlines than everything else?
Sorry, can I tell that Terraria?
So the microphone is for the video, but we still need to speak up. So, oh, okay.
So how can you tell that Terraria has tighter deadlines than compiling the kernel?
The thing is like, usually tasks that voluntarily releases the CPU before their time slice expires, they're latency sensitive. So let's say video games are very cyclic, and how they work, they're very periodic. Usually, in this case, you know, you're supposed to render frames at 60 FPS. So every 1/60 seconds, which is like 16 milliseconds. Every 16 milliseconds, a task needs to run, usually the compositor or Xwayland, needs to run, and it needs to draw a frame, send a frame to the video card. And then it's just sleeping. So latency-sensitive tasks are working in bursts of CPUs, and they sleep. So if you model a deadline that prioritizes these tasks that have this sleepy behavior. And you can do that by, for example, there are many ways. One is measuring out the average runtime between like a wake up and a sleep. If this average time is very short, you're probably facing a latency sensitive task. And you can model the deadline as like, you can use a vRun time, which is a proportional fair share, and you add, for example, this average runtime. So if a task is using a small amount of time, it would get a smaller deadline. And if a task is like a Clang that is built in the kernel, it would use its entire CPU, its entire time slice. So its deadline will be longer. And with this trick, you can prioritize the latency sensitive. It doesn't work every time, but it's the best. I mean, you would need to predict the future to write the best deadline-based algorithm, but that's the best you can do.
I imagine that you need some context switches between the BPF.
Wait. I won't be able to understand.
Oh, okay.
I'm coming here.
Okay.
It's easier.
So I imagine that you need some context switches between the kernel space BPF and the user space scheduler, right? Yeah. So how much of an overhead is it?
Yeah, so, yes, good question. Of course, the user space scheduler is a task in its own, so there are context switches when you need to do scheduling, when you need to do scheduling decisions. I mentioned, like, almost at the beginning, that the scheduler itself is not a CPU-intensive application. It works almost like a latency-sensitive task. That means when it needs to run, and then it just stops. It just, you know, the decisions that the scheduler makes are very small. You know, you need to say, okay, this guy goes here, and then I go to sleep. So the context switches at the end are not, they don't impact much on the scheduler itself, but they can impact on the user space applications that are running. Specifically, more interruptions you have, like if you decide to use a fine-grained time slice, like a smaller time slice, you would get more context switches. But this is it doesn't depend on the scheduler. It's based on how small you define your time slice, right? So a shorter time slice would give you probably better performance in terms of responsiveness, but you also have more overhead. So the throughput would be worse, right? And that, you know, the scheduler here is just yet another task that is running in the system. But you have the same problem with the in-kernel scheduler, because at some point the in-kernel scheduler would also run with the same constraint.
Yes, but the point is that while running the scheduler, we are making the context switches.
While running the scheduler, the same happens with the in-kernel scheduler. Because, you know, you have, okay, you're like, I'm not switching to another task.
You are switching from kernel.
Oh yeah, I see what you mean. Yes, I'm switching to a different task. Yes, that's correct. So potentially that could be like the context switch penalty is bigger with this approach. Yes, that's correct.
So I have a question with regards to, yeah. No, it's okay. Okay, I can speak louder. How do you ship SX Rusland core? For example, so there are two questions behind. Your BPF program, is it written in Rust or not? Or is it a C program?
No, okay. That's
And
another
second
good question.
Okay,
Yeah.
wait a moment. And second question, do you ship a blob in the crate, or is it built? How do you build it?
Yeah, so the BPF part is currently written in C, and what I ship is the .c, which is compiled, like there's a build.rs that calls Clang and compiles the BPF part. And then it becomes BPF bytecode in your machine when you build it, and that's how it works. I'm looking at, there's a library called Aya that generates BPF code directly. So I was investigating if that would be probably better, because everything would be Rust and then BPF, but that's the bytecode is the backend. And probably it's not like a super polished crate. I'm sure there's something that is not, even if it passes like the cargo test and everything, but I'm not sure if it's properly polished, because I'm shipping the .c as an artifact that is included in the crate, which is compiled when you build your scheduler. But
Yeah, so it's not a relevant
for any reason, if the user space scheduler is blocked, the whole scheduling in the system won't progress. Like everything would be deadlocked and blocked. One thing is like page fault. Let's say you do allocations in the user space scheduler, and you hit the page fault. In order to resolve the page fault, you need to schedule a kernel thread. But the scheduler is the guy that is blocked, so there's a deadlock. That's a problem, but that was solved. I solved this one using by M-locking all the memory of the user space scheduler. So the back end is actually M-locking all the memory. You can do allocation. It's just they will happen in an arena of pre-allocated memory. And I'm using the, how's it called, the global alloc, which is an abstraction that allows you to redirect all the allocations. That was really cool. I didn't know that. I learned this in Rust, and I was like, oh, Rust is the best. Because I can redirect like all the allocations into whatever algorithm I want to use to do allocations. And I did this trick to solve the page fault problem.
Okay, if you have further questions, please find Andrea in the hallway, or we don't have a hallway, I guess. But thank you very much.